A continuation for our discussion for fluid mechanics. This is buoyancy from the Archimedes principle. So when it comes to civil engineering board exam, we have two main cases. The first one, for example, we have an object that is not exposed to any liquid. So we'll be having its, let's say, the weight in air, or this is the actual weight. Okay, then if this object is now exposed to a liquid, most of the time water, and let's say that this object has a specific gravity, let's say the specific gravity of the object is greater than the specific gravity of the liquid, it will surely submerge. Then we'll be having the weight submerged. So take note that the weight submerged is not equal to the weight in air. So basically, that is because if an object is exposed to a liquid, I will be having an uplift pressure, that is the buoyant force. Applying mechanics, this is summation of forces vertical equal to 0. Upward forces to be positive, for example, is the same as we have the weight in air less the effect of the buoyant force that will give us the weight submerged. How do we compute buoyant force? So buoyant force is basically equal to the unit weight of the liquid multiplied by the volume of the object. Take note, we are dealing with the total volume of the object since it will be fully submerged. So usually this is the one of the cases. Then our second case, for example, we have an object. Let's say this object has a specific gravity that is less than the specific gravity of the liquid. It will float. The object will float. So this object has its own weight. Let's say this is the weight of the object, and so why does this object float? That is basically we have a buoyant force. For this case, if you are to do summation forces vertical equal to 0, upward forces to be positive, for this object to be in equilibrium, basically the weight is simply equal to the buoyant force. And how do we compute for the buoyant force for this case? That is the unit weight of the liquid multiplied by the volume submerged. Take note that we are just dealing with the submerged portion of the object. So this is the volume submerged. And the weight of the object is basically equal to the weight of the liquid replaced. So these are the two main cases of buoyancy in civil engineering board exam. So let's have an example. So let's have this example. A block has a mass of 400 kilograms in air. So when submerged in seawater, so let's say the specific gravity of seawater is 1.03. It weighs 2,943 newtons. What is the specific gravity of the block? So how do we compute for specific gravity? So basically specific gravity, the specific gravity of the object is basically equal to the unit weight of any object divided by the unit weight of water, or that is the density of any object divided by the density of water. So we need either the density or the unit weight of the object. So we have the given, that is the mass. Okay, we have a mass of 400 kilograms. Take note that mass is constant. Its mass in air is the same as its mass submerged. From this value, we'll be having the actual weight of the object, or we can have it as the weight in air. That's equal to the mass multiplied by the acceleration due to gravity. This is equal to 400 kilograms multiplied by 9.81 meters per second squared. So what is that value? It's 400 times 9.81 is equal to 3,924. So we have the weight in air is equal to 3,924. Kilogram meter per second squared is the same as the newtons. This is the case that the object will be fully submerged. So if the object will be fully submerged, we can have mechanics, summation forces vertical equal to 0. that is the weight in air, okay, less the effect of the buoyant force, okay, will give us the weight submerged. Okay, so what is the weight submerged? Okay, from the problem, the weight submerged is equal to 2,943 newtons. So what is the value of the weight in air? We have 3,924 minus the buoyant force is now equal to 2,943. We can have the value of the buoyant force. So we have, what is 3,924 minus 2,943. Okay, we have that as 981. Take note, our unit here is newtons. So we have the magnitude of the buoyant force is 981 newtons. So if it is fully submerged, how do we compute for the object's volume? Okay, if it is fully submerged, okay, we can compute the volume of the object. So we have buoyant force is equal to the unit weight of the liquid multiplied by the volume of the object. This is equal to 981 newtons is equal to, what is the unit weight of the liquid? Okay. Take note that we have a specific gravity. This is seawater. Okay. A specific gravity is equal to 1.03. So therefore, the unit weight of the liquid will be equal to its specific gravity of the liquid 1.03. This is 1.03 multiplied by gamma water. Take note, this is newtons. So we are using 9,810 newtons per cubic meter, then multiplied by the volume of the object. If we are to do unit analysis, cancelling newtons, the remaining unit will be cubic meter since it is volume. So what will be the volume of the object? So let's have it as that is equal to 981 divided by 1.03 of 9,810 newtons per cubic meter. So we have the volume equal to 0.090. We can have it as 0.097 cubic meter. So what is next? Since we have now the volume of the object, we can have its density or the unit weight. So let's say I'll be using the unit weight first. A unit weight of the object is basically equal to the weight of the object divided by the volume of the object. Take note, we are to use the actual weight, which is the weight in air. That is equal to, we have 3,924 newtons. This is divided by the volume of the object is 0.097 cubic meter. So what will be the unit weight of the object? A unit weight of is equal to 3,924 divided by 0.097. So it's equal to 40, what's that value again? 40,453.608. Newtons per cubic meter. So let us see. 40,453.608 newtons per cubic meter. So how do we compute for the specific gravity? This is equal to the unit weight of any object divided by the unit weight of water. This is 40,453.608 newtons per cubic meter. So take note that our divisor should have the same unit. That is the 9,810 newtons per cubic meter. So let's have that value. This is the answer divided by gamma water 9,810 equal to, so specific gravity of 4.124. 4.124. So take note, specific gravity is unitless. Okay, let us check on our choices. Okay, so we have the value, our closest value is letter C. This is 4.12. So that will be our answer. So again, we can also have the value of the specific gravity using density if we are to use the mass. That is our solution for problem 14. Alright, so let's have this example. This is a problem from our board exam. Number 15, a hollow cylinder 1.1 meters in diameter and 2.4 meters long weighs 3,825 newtons. How many kilonewtons of lead weighing 110 kilonewtons per cubic meter must be fastened to the outside bottom to make the cylinder float vertically with 1.9 meters submerged in fresh water? So our liquid this time is simply water. So its specific gravity is simply equal to 1. So always start with mechanics. So what are the forces involved? So this is our tank. The depth submerged is 1.9 meters. The diameter is 1.1 meters. So what are the forces? Let's have first the weight of the cylinder, which is equal to 3,825 newtons, or we can have it as 3.825 kilonewtons. Then also, we are to consider the weight of this as lead, which is fastened outside the tank or the cylinder. So let's say this is the weight of the object. So the cylinder will float, having the lead attached to each bottom. Take note, we have two objects exposed to water. So therefore, we'll be having two buoyant forces. So what are those buoyant forces? Let's say we have buoyant force number 1, that is the buoyant force for the cylinder. Then we have buoyant force number 2, that is the buoyant force for the lead. So for mechanics, this is summation of forces vertical equal to 0. This is buoyant force number 1 plus the buoyant force number 2 is equal to the weight of the cylinder plus the weight of the lead. We say the weight of the object. So how do we, again, we are to recall what are the basics. So we have the equivalent of gamma is simply equal to the weight of the object divided by the volume of the object. Then buoyant force is simply equal to the unit weight of the liquid, then the volume submerged. Or we can have it for the case of the lead, the unit weight of the liquid, volume of the object. Okay, so let us now compute for the volume of the lead first, since we don't have yet the volume of the lead. It's not given, only the unit weight. So how do we compute for the volume of the object? Again, gamma, or the unit weight of the object, is equal to the weight of the object divided by the volume of the object. We can have the weight of the object as the unit weight of the object multiplied by its volume. Buoyant force number 1, that is the buoyant force against the cylinder. Take note, the submerged depth is only 1.9 meters. That is the unit weight of water, unit weight of liquid, 9.81 kilonewtons per cubic meter. What is the volume submerged for the cylinder? We have a diameter of 1.1 squared pi. This is divided by 4. The submerged depth is only 1.9 meters. This is in terms of the cubic meter. Then plus buoyant force number 2. So that is gamma liquid, 9.81. What is the volume of the lead? We don't know the volume of the lead. It is not given. So let's say this is IB sub O, 9.81 times IB sub O. And this is now equal to, the weight of the cylinder is given as 3.825 kilonewtons. Then plus, again, we don't know yet the weight of the lead. But weight is unit weight, that is 110 kilonewtons per cubic meter, multiplied by the volume of the object. So gamma If we are to recall, this is gamma object, okay, multiplied by the volume is equal to, okay, the weight of the object. Okay, in this equation, the only unknown is the, okay, we are looking for the volume of the lead. So let's have that, okay, we are to use ship solve. This is 9.81, then multiplied by, this is 1.1 squared, multiplied by pi, divided by 4, then multiplied by the depth submerged, that is 1.9, plus gamma water, that is 9.81, multiplied by the volume of the object, we say alpha, alpha x, is equal to, what is the weight of the cylinder? That is 3.825 kilonewtons, plus the unit weight of the lead, 110. This is multiplied by the volume of the object, unknown, alpha x. Then we do ship solve. So we have the volume of the object is 0.139. Okay, we use 0.139. The volume of the lead needed is equal to 0.139 cubic meter. So again, how do we compute for the weight? Weight is the unit weight of the object, volume of the object. Unit weight of the lead is 110 kilonewtons per cubic meter. The required volume is 0.139 cubic meter. So let's have the weight of the lead. We have the weight of the object is equal to, so maybe we can use the stored value. So answer multiplied by 110 kilonewtons per cubic meter. So we're having a value of 15.248. This is 15.248 kilonewtons. Kilonewtons. Let us check on our choices. Okay, so we have the closest value is, we have letter D. This is 15.24. So this will be our solution for problem number 15. Take note that if we are solving buoyancy, take note that we are just applying some of the basic concept of mechanics. That is simply the summation of forces vertical equal to 0. And when it comes to fluid mechanics, take note that we are just using the fundamental properties. That is, the unit weight, the density, the specific gravity. And we can have, we are using the mass, the weight, then the volume. Okay, so this we are just using this basic concept, the fundamental properties. So this will be our solution for problem 15. Okay, so we continue to relative equilibrium. So this is the study of liquids in a moving container. So for example, we have this tank that contains a liquid, and for example, this tank is at rest, or if it is, for example, if it is moving, but with a constant velocity. So if the velocity is constant, that is the same as acceleration equal to 0. So if we have a velocity constant and acceleration equal to 0, the liquid surface will be horizontal. Okay, so what about if we have this case, if the tank is now accelerating to the right, so let's say the acceleration is now greater than 0, what will happen to the liquid surface? So we'll be having an inclination of the liquid surface for a reason. Okay, the liquid particles will be compressed at the back of the tank. So how do we compute for this liquid surface inclination? Let's say theta. So for example, we are to get one particle of water or this liquid. So this particle of liquid, so we are getting one particle. This particle of liquid has its own weight. And if it is accelerating or affected by acceleration, it is acted by the REF. This is the reverse effective force or the inertial force. Based on second law of motion by Newton, this is the mass times acceleration. Then these two forces will be having their corresponding resultant. So let us draw the corresponding force triangle. So we have weight is always downward. This is the weight. If the acceleration is horizontal, the reverse effective force is also horizontal, opposing the motion. Then their corresponding resultant force. Okay, so we have the angle between the weight and the resultant is the theta. Okay, what function can be used? For example, I'll be using tangent. Okay, the tangent of theta is basically equal to opposite, that is the reverse effective force, divided by the adjacent side, that is the weight. What is the equivalent of REF? That is the mass times acceleration. Equivalent of weight is the mass times the acceleration due to gravity. So we can cancel mass. So we'll be having the tangent. The tangent of theta is now equal to the acceleration divided by the acceleration due to gravity. So this will be our equation. In the computation of the inclination of the liquid surface if the container is accelerating. Okay, so let's have one example. Okay, so let's have this example. An open rectangular tank mounted on a truck is 5 meters long, 2 meters wide. So kindly imagine we have a tank that is 2 meters wide perpendicular to the paper and 2.5 meters high, is filled with water to a depth of 2 meters. So the height of water is 2 meters. So number 16, what maximum horizontal acceleration can be imposed on the tank without spilling any water? So we have a free space. If you are to analyze, we have a free space of 0.5 meters. 0.5 meter. This is the available free space inside the tank. Since the height of the tank is 2.5 and we have an available of 2 meters water. So without spilling any water, it is expected, for example, this tank will accelerate to the right. The water will be compressed at the back or on the left side of this tank. So what will happen to the liquid surface without spilling? So we assume that the water will only reach the opening of the tank. Or basically, we will be having a rise of liquid surface at the back, which is equal to 0.5 meter. So for number 16, we are just to relocate this portion, this water. This water will be moved at the back. Let's say they will move or they will be compressed at the back of the tank. If without spilling, basically we are just relocating liquids. We have a rise of water at the back of 0.5. Therefore, we'll be having a decrease in height of water surface in front with a distance of with a height of 0.5. Since it is asymmetrical, we are just to consider this triangle. Having a height of 0.5, so symmetrical. This is 2.5 meters, just the half of the length. Half of the length, which is equal to 5 meters. So we are just to consider this triangle. Having a height of 0.5 and a length of 2.5 meters. Then we are looking for this angle theta. So we can use the function. That is, we have the tangent of theta is equal to the acceleration divided by the acceleration due to gravity, which is also equal to, if we are now to refer to this triangle, the opposite is 0.5. The adjacent side is 2.5 meters. So we can now compute for the acceleration. We are just to consider these terms. That is the acceleration divided by acceleration due to gravity. This is 9.81 equal to 0.5 divided by 2.5. So computing for the acceleration, we have that is the same as 9.81 multiplied by the ratio of 0.5 divided by 2.5. So we have that acceleration is now equal to We have an acceleration equal to 1.962. This is in terms of meters per second squared. So this will be our answer for question number 16. If we are to check on our choices, 1.962, that is, we have letter A, 1.962 meters per second squared. Then we proceed to problem 17. If the acceleration is increased to 6 meters per second squared, how much water is spilled out? Okay. So since the maximum acceleration without spilling is only 1.962 meters per second squared, so obviously for problem number 17, so this is the acceleration is now equal to 6 meters per second. So there will be spilled water. What will be the appearance of the liquid surface or the liquid inside the tank? So there will be two assumptions. So the first assumption is that the liquid surface, the front edge of the liquid surface, will be still in touch with the front wall of the tank. That is one assumption. The other assumption is that if we assume that 6 meters per second squared is a very high value for an acceleration, possible that the front edge of the liquid is already on the floor of the tank. So these are our two possible assumptions. Okay, so I'll be using the second assumption. I'll be assuming that the front edge of the liquid or water is already on the floor of the tank. So this will be the, let's say, the remaining volume, let's say V sub R, volume remain. The remaining volume of water inside the tank. So how do we prove that this is the correct assumption? So let us first determine this dimension, let's say x. For correct assumption, the value of x should be less than the length of the tank. So it should be less than 5 meters. So we are using our equation, that is the tangent of theta is equal to the acceleration divided by the acceleration due to gravity. So let's say this is our angle of inclination. This is theta. What is the opposite side for this triangle? The opposite side is equal to 2.5 meters. Divided by adjacent side. Our adjacent side is the value of x. So we are now to substitute. What is our acceleration? That is 6 meters per second squared. Divided by acceleration due to gravity. This is 9.81. Is equal to 2.5, the height of the tank, divided by the value of x. So computing for the value of x, so we'll be having the value of x is equal to, that will be 9.81, multiplied by 2.5. This is divided by 6. So that will be 9.81 multiplied by 2.5 divided by 6. So we have that as equal to 4.0875 meters. 4.0875 meters. So if we are to recall, how do we prove this one? It should be less than 5 meters. So therefore, our assumption is correct. The length of the tank is 5 meters. We assume that the front edge of the water is already on the floor. We have the value of x as 4.0875 meters. It is less than 5. So how do we compute for the volume remain, or the remaining volume of the tank? So we recall that the width of this tank perpendicular to the paper is 2 meters. So let's have the volume remain So we have volume remain is equal to 1/2. What is our base? This is 4.0875 meters. Then what is the height? The height is equal to 2.5 meters. Perpendicular to the board or to the paper, that is, we have 2 meters. So let's have the volume remain. That is 1/2 of 4.0875 multiplied by the height of the tank, that is 2.5 meters, multiplied by perpendicular to the board, it is 2 meters wide. Okay, so we have the value 10.21875. So we have 10.21875 cubic meter. How do we compute for the volume spilled? So volume spilled, that is the required for problem 17. Let's say B sub S, the volume spilled is basically equal to the initial volume minus the volume remain. If we are to recall our initial figure, what is our initial height of water? The initial height of water is 2 meters. So it is, the height of water initially is 2 meters. It is 5 meters long and 2 meters wide, perpendicular to the paper. That will be the volume initial. So let's have the volume spilled. What is our initial volume? That is 5 meters long, 2 meters high, and 2 meters wide. That will be our initial volume minus our volume remain. That is equal to 10.21875 cubic meters. So let's have the volume volume spilled. So volume spilled is equal to, so basically the product of this term, 5 times 2 times 10 times 2 is 20. So that is the same as 20 minus, let's say 20 minus the answer. Okay, so we have the volume now is equal to 125 cubic meters. So this is the volume of spilled water. So let us check on our choices for problem 17. We have letter C. That is equal to 9.78. So that will be our solution. So again, if we are to just to make it clear, how do we compute for spilled volume? That is the initial volume of water minus the volume remain. So this will be our solution for problem 16, 17. So we proceed to rotating vessel. So for example, we have this tank that contains liquid to a certain height. Then, for example, we are to rotate this tank about its axis, let's say with a speed of omega, or this is the angular velocity, usually in RPS, or this is the radian per second, or we can have it as the revolutions per minute. So what will happen to the liquid surface? So the center of the liquid surface will go down, and on the circumference, the liquid surface will go up. So it will form an airspace with a height of, let's say, with a height of h. This is the height of the paraboloid with a formula of omega squared, the radius squared divided by twice the acceleration due to gravity. So take note that this airspace is the paraboloid. How do we compute for the volume of a paraboloid? So let's say this is the B sub P. The volume of paraboloid is equal to 1/2 pi the radius of the tank squared times its height. So this is the formula for the volume of a paraboloid. So let us have an example for rotating vessel. So let's have this example for problem 18 to 20. So an open cylindrical tank 3 feet in diameter and 5 feet high is 3/5 full of water. So 3/5 of 5 is 3 feet. So obviously we have a height or a depth of water equal to 3 feet. If the tank is rotated about its vertical axis, number 18, what angular speed should it have so that the water would just reach the rim of the tank? That will be question number. This is question number 16. So if we are to rotate this tank, then what will happen to the liquid? The liquid will just reach the opening of the tank. So this will be the appearance of the paraboloid. Okay, so this is the case of without, for number 16, this is without spilling. I take note for the case of without spilling, I take note that this will be the behavior of the height of the paraboloid. Half of the height of the paraboloid will go down, will be equal to half of the height of paraboloid will go up. Okay, so this will be the behavior of the paraboloid if our case is again without spilling. So this height is half of its height for the paraboloid. This downward movement of the water, or if the center of the liquid surface will go down, without spilling, it is allowed to go down at a depth of h over 2. So by the way, what is our free space? Our free space earlier is equal to, we have a free space of 2 feet. So therefore, what is the equivalent of h over 2? Basically, the equivalent of h over 2 is equal to the free space, that is 2 feet. Or we may actually reword the question, what angular speed should it have so that the water would just reach the rim of the tank? That is the same question as what is the maximum angular velocity without spilling water? Okay, so therefore, what is the required height of paraboloid? So the required height of paraboloid is 2 times 2. The required height is equal to 4. This is 4 feet. Okay, what is our formula for the computation of the height of a paraboloid? This is the height equal to angular velocity squared, the radius squared divided by 2 times the acceleration due to gravity. Again, if we are to recall what is the diameter of the tank, that is 3 feet in diameter. Therefore, we have a radius of 1.5 feet. Okay, a radius of 1.5. So let us now compute for the angular velocity. So the required height of the paraboloid is 4 feet, equal to the angular velocity squared, a radius of 1.5 squared. This is divided by twice. Take note, we are in English units. So what is the acceleration due to gravity in English? That is equal to 32.2. So we'll be having the angular velocity in the radian per second. If we are to do unit analysis, it will be radian per second. So this is, we have 4 is equal to, that is alpha x for the unknown, the angular velocity, squared. This is multiplied by the radius, that is 1.5 squared. Divided by, this is twice, acceleration due to gravity, English, that is 32.2. So I'll be using strip solve. So we'll be having the angular velocity is equal to 10.699 radian per second. If we are to check that on our choices, that is equal to, we have letter A, that is 10.7. For problem 19, what speed should it have so that the depth of water at the center is 0? What will be the appearance of the paraboloid for that case? The appearance of the paraboloid, obviously, we may assume that the vortex of the paraboloid will be at the center of the bottom of the tank. So this is the appearance of the paraboloid. So for this case, what is the required height of paraboloid? So the required height of the paraboloid is the same as the height of the tank. Okay, the same as the 5 feet. Okay, so for number 19, okay, we have the h is equal to angular velocity squared, the radius squared divided by twice of acceleration due to gravity. For problem 19, the required height is the height of the tank. We have 5 feet equal to angular velocity squared. The radius of the tank is 1.5 squared. This is divided by twice of 32.2. So we'll be having the angular velocity. So this is 5 equal to, this is, let's say we are using alpha x squared multiplied by the radius, that is 1.5 squared. I divide by 2 times, again, English unit, this is 32.2. Then I'll be using shift solve. So we have an angular velocity equal to 11.963. 11.963, the radian per second. But if we are to observe the unit of our choices, the required unit should be in RPM, or that is the revolutions per minute. So all we have to do is convert this one. So we are multiplying. This is 2 pi radians is the same as 1 revolution. Then multiplied by, this is 60 seconds is to 1 minute. So if you are to do unit analysis, the remaining units will be the revolutions per minute, or the RPM. So we have the angular velocity is now equal to, so 11.9629, I'll be using the stored value. This is multiplied by 60 divided by 2 pi equal to, so we'll be having a value of 114.237 to 37. So 114.237 revolutions per minute, or the RPM. If we are to check on our choices, for problem number 19, so 114.2. So the closest value is, we have letter, that is letter C. And last question, number 20. What speed should it have so that there is no water at the bottom 1 foot from the vertical axis? Okay, so for problem number 20, for example, this is the vertical axis, the red line. The required is that there will be no water at a distance of 1 foot from the vertical axis at the bottom of the tank. So the appearance of the remaining water inside the tank will be like this. Okay, so the appearance of the water will be an incomplete, or the appearance of the air inside the tank will be an incomplete paraboloid. So this green pen will represent the water. So this distance is 1 foot. 1 foot from the vertical axis, 1 foot from the vertical axis. So how do we compute for the required angular velocity? So take note, if we have an open tank and we have an angular velocity that will cause an incomplete paraboloid, all we have to do is extend the paraboloid under the tank. But this is only an imaginary portion of the paraboloid, just to have a complete analysis. So let's say this is h sub 1, the height of the bigger paraboloid, h sub 1, and the paraboloid, the imaginary paraboloid under the tank is our h sub 2, the smaller paraboloid. Take note, this is just an imaginary paraboloid, just to complete the analysis. Take note, it is purely imaginary. So what is the radius of the larger paraboloid? That is the same as the radius of the tank. 1.5 feet. It should be 1.5 feet. And the radius of the smaller paraboloid, which is the imaginary paraboloid, is the given distance of water from the vertical axis. That is the 1 foot. So all we have to do is, okay, determine the equivalent of H1. What is the equivalent of H1? Okay, we have the height of the tank as 5 feet plus the height of the imaginary paraboloid. That is 5 plus h sub 2. That will be the equivalent of H1. So we are applying here the concept of SPP. This is the squared property of a parabola. Take note that the plane figure equivalent for paraboloid is the parabola. So we are using the squared property of a parabola. So that is the same as the, we have the R1 squared is to h sub 1 is equal to r sub 2 squared is to h sub 2. Okay, so from our figure, what is our R1? So R1 is the radius of the bigger paraboloid. That is the same as the radius of the tank. Okay, we have 1.5. Okay, this is squared divided by H1. What is the equivalent of H1? H1 is the same as 5 plus h sub 2 equal to r sub 2. R sub 2 is the given 1 foot. That is 1 squared divided by h sub 2. H sub 2 is unknown. So we are computing for h sub 2. That is the height of the imaginary paraboloid. Okay, so we have, that is a 1.5 squared is to equivalent of h sub 1. That is 5 plus the unknown. Let's say alpha x for h sub 2. Okay, that is equal to, okay, we have the radius of the smaller paraboloid, that is 1 squared, is to the unknown alpha x h sub 2. Then we are doing shift solve. Okay, what is the height of the imaginary paraboloid? Oh my God. What's happening on our calculator? It's not giving a proper answer. So we are just to retype. Before we press equals, if you're using shift solve, we may assume a value or a close value to the expected value before pressing equals. So it's 1.5 over 5 plus we have alpha x is equal to so shift solve. Before we press equals, we may assume a value close to what is expected. Let's say I'll be expecting a value of 3. Then press equals. Okay. So the value will be equal to, this is 4 feet. That is 4 feet. So therefore, can we have now h sub 1? H sub 1 is equal to 5 plus that is 5 plus h sub 2, which is 4. So which means the total height of the big paraboloid is equal to 9 feet. That will be the equivalent height of the big paraboloid. So we may use h sub 1 equal to angular velocity squared r1 squared divided by 2g. If I'm using h1, I'll be using r1. If we are using h sub 2, then we should use r sub 2. It will give the same angular velocity. So our h sub 1 is 9 feet equal to the angular velocity squared multiplied by radius 1. That is 1.5 squared. This is divided by twice of 32.2. So let's have the angular velocity. We have 9 is equal to so this is 9 is equal to the angular velocity squared multiplied by the radius. We have 1.5 squared. This is divided by twice of 32.2. Then we do a shift solve. So we have that as 16.0499. 16.04 99. This is in terms of the radian per second. We are converting this one to RPM. All we have to do is multiply it with 60 over 2 pi as per on our previous problem. So multiplying this value, the stored value, multiplied by 60 divided by 2 pi, so that our answer will be in RPM, or the revolutions per minute. Okay, so we have 153.265. So angular velocity is equal to 153.265. Now RPM, or the revolutions per minute. So this will be our answer. If we are to check that on our choices, we have 153.265. Our closest value is 153.3, letter D. So this will be our solutions.